Okay, our last section for the first class is section 1.4, which discusses real numbers and the number line. And this is pretty in-depth. There's a lot of stuff going on in this section, just some fundamental mathematics skills and arithmetic skills that you need to know about and you need to remember for the duration of your mathematic career. So the first thing we want to talk about is our additive inverse, which is basically the opposite of a number, right? So if I say 5, right, the additive inverse of that is -5. Now on the flip side, if we have -7, the additive inverse of that, well, the opposite of -7 is +7. Basically, you're saying the opposite of the opposite of 7, which is where our double negative rule comes in. Our double negative rule says that if we have the opposite of a number, or a negative a, it ends up kind of canceling each other out. Kind of like, you know how a double negative in language is a positive? Don't not do that, right? That means do that. So they sort of cancel each other out. So example 1a, we're just asked to find the opposite or the additive inverse of each expression. So the opposite of 13 is -13. The opposite of -4/7 is +4/7. And then the opposite, now this one's a little bit weird because it's not completely simplified to start off with. So let's simplify that first. First off, we have a negative and a negative, which cancel out to really give us 7. So we're saying, what is the opposite of this? What is the opposite of 7, which is -7? Now, another way we could also think of that is, what is the opposite of -7? So that's the negative of the negative of -7. You can think of it as 2 of the negatives canceling out and still having 1 left over. But that's really getting more complicated than we need to. Simplifying it first and then finding the opposite is much easier. Along the same lines, dealing with our additive inverse, find the additive inverse of -t if t equals -2/3. So we have to be careful with this. It says find the additive inverse, or the opposite, of -t. So the first thing we have to do is we have to evaluate, well, what is -t? Negative t is -2/3. So we need to simplify this. Well, our two negatives cancel out. The additive inverse of -t, what's the additive inverse of 2/3? Well, the additive inverse of 2/3 is -2/3. That one's kind of makes you think a lot, especially for the end of class. But really, the idea is simplify this first. -t is -2/3, which becomes a +2/3. So when it says find the additive inverse of -t, it's really saying find the additive inverse of 2/3. Okay, let's move on before we dwell on that a little too much. Now, we've talked about natural numbers, we've talked about whole numbers. Now we're going to talk about different other kinds of numbers. We're going to talk about these things called rational numbers. And rational numbers are any number that can be expressed as a fraction. Okay, so in other words, well, fraction that you can think of is 1/2. Hey, look, that's a rational number. But it doesn't always have to be specifically a fraction. It just can be expressed as a fraction. So a number like 5 is also a rational number because you can express it as 5/1. A number like 1.2 is also a rational number because you can express that as 6/5. You just have to be able to express it as a fraction. So it says classify the numbers. Classify each number as one or more of the following: natural, whole, integer, or rational. Oh, we haven't talked about integers, have we? We have not. Oh my goodness, I can't believe I forgot about that. Let's add that in right here. So an integer includes natural numbers, 0, and the opposite of natural numbers.
Hoku.
Oh, hi, honey.
Come here.
Oh, you're wet.
Come here.
And the opposite. Sorry, that's Hoku. Opposite of, I'm squishing, natural numbers. Okay, let's get that all in screen there. So again, we have natural numbers, which are counting numbers, whole numbers, which are counting numbers including 0, integers, which are natural numbers, 0, and the opposite. So it's positive and negative whole numbers basically, but you can't have a negative 0, so we don't necessarily say positive and negative whole numbers. Anyway, so we want to go ahead and express these values as natural, whole, integer, or rational. So here we have 12/4. First off, it is a fraction, so we can definitely classify it as rational. But we can also look at this and say, well, 12/4 can be simplified to just become 3, which is a natural number. It's also part of the whole number family and integers. So this value, 12/4, is not only rational, it's also natural, whole, and an integer, if I could squeeze that in there. Okay, what about -3? Can you express -3 as a fraction? Yes, look at that. -3/1, ta-da, I did it. So it's definitely rational. Okay, is it a natural number? Is it part of your counting number family? If you start counting, are you going to count -3 in there? No. Because it's not part of natural numbers, it's definitely not part of whole numbers, so that's out. Integers are natural numbers and whole numbers, but they're also the negative, the opposites of them. So -3 is rational, and it's an integer. What about 0? What about 0? What about 0? What about 0? So 0, is it a natural number? Do you count it? No. Is it a whole number? Yes, because whole numbers include 0. Is it an integer? Yes, because by definition, an integer includes 0. And can you express this as a fraction? Hey, look. 0/5. Hey, look, it's a fraction. So it's also rational. And then the last one, -9/5. So again, is this a natural number? Do you count -9/5 when you count? No, I sure don't. Because it's not a natural number, it's definitely not a whole number. Integers are positive and negative natural numbers. That's definitely not a natural number, so an integer is out. And then a rational number is any fraction. Here we go, it's a fraction. So -9/5 can only be expressed as a rational number. Okay, the last part of this page. Square roots. So the square root, it says the number b is a square root of a if b squared equals a. So this one's sort of abstract, the way that we think about this. An easy way to explain it is, hey, what is the square root of 100? A lot of people just say 10. But every square root not only has a positive number, but it also has, every square root not only has positive square root, but it also has a negative square root. So not only is it 10, but it's also negative 10. And instead of saying positive 10 and negative 10, we can use a fancy symbol. This says plus or minus 10. You'll see this a lot in Math 1105. Something good to have the idea of. In my math lab, it does insist that you write them separately, 10, comma, negative 10. So it says every positive number has one negative square root, negative 10, and one positive square root, positive 10. Now, the positive square root is also called the principal square root. And that's really the square root that you've grown up dealing with and learning about. Hey, what's the square root of 25? 5, right? Not a lot of times you don't really think of negative 5 as the answer, even though it is. So, evaluate each square root, approximate your answer to 3 decimal places when appropriate. So, first, example 4a, we have the square root of 36. Well, the square root of 36 is plus or minus 6, positive 6 and negative 6. Now, it does say up here calculating the principal square root. So we do want to identify, okay, the principal square root is just 6. So be aware that you do have 2 answers, but for our purposes for right now, we're only going to be working with our principal square root. Again, hey look, we have a square root of 100. Square root of 100 is principal square root 10. And then the square root of 5. I don't know about you, but I don't think I can do that evenly. I know I can take the square root of 4 evenly. I know I can take the square root of 9 evenly. But the square root of 5 is definitely not possible. So I'm going to get my scientific calculator, and I'm going to take the square root of that. I wonder if you could see my calculator. Hey, you can see that pretty well. I'll move it down a little. So I'm going to take the square root of 5, just press enter. I get this really, really, really long decimal here. It says, though, to only round to 3 decimal places. So that's the tenths, hundredths, and thousandths spot. So after that, the 4th decimal place is a 0, which means that we're going to keep the 6 the same. So that is approximately, we'll use 2 squiggly lines to say approximately equal to show that we're rounding, 2.236, because it's not exact. Every single one of these are completely exact. We want to talk about more types of numbers. We've talked about natural numbers, whole numbers, integers, rational numbers. Now we're going to discuss real numbers. And you're like, what? If they're not real, are they fake? Well, later on in 1105, Math 1105, we learn about imaginary numbers. For right now, we're just going to work with real numbers. A real number is any number that can be represented by a decimal. That's it. Any number that can be represented by a decimal. So an example of a real number, well, what have we learned about? 5. I like the number 5. Negative 17, that could be represented as decimal. 4/5. Radical 7. Negative radical 3. Oh, I should also say, in addition to calling this a square root sign, you can also call it a radical. If you have questions about that, feel free to ask it in class. A mixed number could be a real number, 21 1/3. And then a decimal, 57.63. Now, if a number is real, but you can't necessarily express it as, a fraction or a radical, you also have these things called irrational numbers, which is still a part of a real number. Irrational numbers are numbers that cannot be expressed by a fraction. So we have rational numbers and irrational numbers. So an example of an irrational number is something like, pi. Pi we approximate as 3.14. Of course, it's longer and it's never ending, but that's what we can approximate it as, 3.14. The numbers up here that are square roots, radical 7, negative radical 3, all of those are irrational numbers, numbers that cannot be expressed by a fraction. What else do we have hiding here? Okay, classifying numbers. Identify the natural numbers, whole numbers, integers, rational numbers, and irrational numbers. You know what? Before we do that, let's discuss how all of these different types of numbers, whole numbers, natural numbers, integers, rational numbers, and irrational numbers, all relate to real numbers. Well, all of these different kind of numbers are all in the family of real numbers. So let's get all that up there. Here's our real number family. So this represents all real numbers. Now the last type of numbers we talked about were irrational numbers. We said irrational numbers are numbers that cannot be expressed with a fraction, whereas rational numbers are numbers that can be expressed with a fraction. So we're going to have two blocks inside of here. One for irrational numbers and one for rational numbers. Then within rational numbers, we have integers, then inside of there we have whole numbers, and inside of there we have natural numbers. Basically what this is saying is if you have a natural number or a number that is a natural number like 5, not only is it a natural number, it's also a whole number, an integer, a rational number, and a real number. So you can sort of build within here, right? Natural numbers, 1, 2, 3, 4, 5, so on and so forth. Whole numbers, 0, 1, 2, 3, 4, 5. Integers are both of these put together, but also the negatives. Rational numbers are anything that can be expressed as a fraction. Irrational numbers, anything that cannot be expressed as a fraction. Okay, so let's use this diagram to help us do example 5. Oh, let's move this up just there so we can see that. Okay, so natural numbers, whole numbers, integers, rational numbers, and irrational numbers. I'm just going to write this out. First, I want to identify all of my natural numbers. So if we look in this list, which numbers are natural numbers or counting numbers? Well, just 9. Okay, so we've used 9. Oh, but wait, 9 is not only part of natural numbers, it's also part of whole numbers. Not only is it a part of whole numbers, it's also a part of integers. And it's also a rational number because we can express it using a fraction. 9 over 1. Is it an irrational number? No, it's not. Let's go ahead and put irrational. Okay, so that's all of our natural numbers, so that's done. Excuse me. Next, we have whole numbers. So if we look here, are any of these numbers now whole numbers? Nope. Okay, so that's done too. Integers, do we have any integers? Positive and negative whole numbers. Yes, we do. We have, oh, I missed something. I wonder if you missed it too. Radical 49. Can we simplify that? Yes, we can. Radical 49 is just 7. So that also belongs in our natural numbers, which also belongs in our whole numbers and our integers and our rational numbers. Oh boy, I missed that one. Okay, so now are we good? Let's double check. Negative radical 5. I can't simplify radical 5, so that's fine. 9, we got that. Negative 3.8, that's not a whole number or a natural number, so I can't do anything with that. Radical 49, we said we could simplify to become 7, so we put that in each of these. A natural number, whole number, integer, and rational number. 11 over 4, nope, that's done. And then negative 41, so we're done with all of our natural numbers and whole numbers. Now what about integers? Positive and negative whole numbers. That's where negative 41 comes into play. And if it's an integer, it's also a rational number. Okay? So now natural numbers, whole numbers, and integers are done. Rational numbers. Again, a rational number is any number that can be expressed as a fraction. So we have one that's very obvious. It is a fraction, 11/4. But we also have this decimal here. Now this decimal is called a terminating decimal, meaning it ends. 3.8. It's not approximately negative 3.8 or negative 3.8 and it's just hiding a bunch of stuff after it. It's only 3.8. So we're going to learn this later, but we could actually write this as a fraction. So for now, we're just going to go ahead and write that in there, negative 3.8. Then the only irrational number we have, the only value up here that cannot be expressed as a fraction is negative radical 5. Oh boy. So now we're going to move on a little bit and discuss this table that we have. It says, the table below lists the number of wireless subscribers in millions in the United States for various years. Find the average number of subscribers for these years. Is the result a natural number, rational number, or an irrational number? First thing we have to do is remember, what is an average? Well, an average takes all of the values you have, it adds it all up, and then it divides it by the number of numbers. So, the subscribers, we have 28, 97, 194, and 292. And how many numbers do we have? 4 numbers. 1, 2, 3, 4. So we're going to add that all up, which gives us 611 over 4. And that is exactly 152.75 million. That's the average number of users from 1995 to 2010. So now that we found that out, what kind of number is that? Natural, rational, or irrational? Because it's a terminating decimal, 0.75, that means that we can express it as a fraction, so it's going to be a rational number. Now that we've learned about all of these different kinds of numbers, natural numbers, real numbers, whole numbers, integers, rational numbers, and irrational numbers, we can talk about the number line. So a number line is, you could sort of think of it as one-dimensional. It either moves left to right, up or down. Typically, we see number lines that move left to right. Normally, in the center, we have 0. And then, moving out to the right, we have positive numbers, positive natural numbers, 1, 2, and 3. Moving out to the left, we have integers, -1, -2, and -3. Now within this number line, that 0 is a really important part. It's called the origin, kind of like the origin of coordinate plane that we'll be talking about later. And we're able to plot numbers on the number line to show the relationship between the numbers. How is -5 related to 9? That's what we're looking at here. That's how the number line helps us to relate numbers. Example 7 asks us, okay, now take all of these numbers and plot them on the number line, just so you can get an idea of their relationship. So I'm just going to make one number line. Now, before I start drawing anything in, I want to know what these numbers stand for. If I look at them, I see weird numbers. I don't really get an understanding for what actual value it is or how they relate to each other. So what I'm going to do is I'm going to rewrite them as a decimal. That's going to be the easiest thing here. So whether you take your calculator or if you just know what -3/2 is, we can take 3 divided by 2. So that gives us -1.5. Decimals are a really good way to relate numbers to each other because decimals are very understandable. Oops. Then we have, oh, maybe if my will fix itself, the square root of 3 is 1.732. And then we have pi, which is right there, and that is 3.142. Okay, now that we can see that, we can go ahead and see, okay, well, how many do we need on the top in our positive numbers? How many do we need on our bottom in the negative numbers? I like to go up to the next whole number that we'll need. So for instance, our lowest number is -1.5, which means I'm going to go down to -2, at least. Our highest number is 3.142, so that means I want to go one above that, so I want to go up to 4, at least. And then we're going to have some even intervals, hopefully, in there. So -1, 0, 1, 2, and 3. And we're going to plot these. -1.5. Here's our -1. 1.5 is in between 1 and 2. Plot them. And I'm not going to write their decimal equivalent. I'm going to write their original, the original way that it was written. -3/2. Okay. Then we have 1.732. So here's 1. 1.7 is more towards the upper half. 1.7, it's almost at 1.75. Again, on a number line, we can approximate as best as we can. That's radical 3. And then we have pi, 3.14, which is just a skosh over 3. So that's plotting on a number line. Oops. Okay. Now, along with all of these values, these types of numbers, and these operations that we're working with, we also have something called absolute values. Now, the absolute value symbols are just 2 bars, like that, on the outside of a number. And the absolute value is really just saying, hey, what is the distance on the number line a number is from the origin? So because we're dealing with a distance, we know that our answer always has to be positive because we can't have a negative distance, right? A distance is just one step to the right or one step to the left. You're not going in a specific direction. You're taking one step either way. So for instance, if we take the absolute value of -2, we have -2, that's 2 steps away from 0, so that's 2. Now, we can also take the absolute value of +2. So +2 is also 2 steps or 2 units away from 0, so that's also 2. Finding the absolute value for each one of these, the absolute value of 3.1 is just the value 3.1. It is 1, 2, 3, and then wherever 0.1 is away from it, 3.1. -7 is how many units away from the origin? 7 units away from the origin. And then the absolute value of 0 is still just 0. It's 0 away from the origin. Now, since we're dealing with the number line and the relationship of numbers, we can use inequalities to help us determine the relationship. An inequality is a statement that 2 or more values, we're going to be dealing with 2, but later on in Math 1105 you'll be dealing with more, 3 values. So it's a statement that 2 values are less than, greater than, here's our greater than symbol, less than or equal to, or greater than or equal to. So for instance, if we're comparing numbers, like if we look at that example up top, oh, you can't see what I want to write. If we're looking at that example up top, we have -3/2 and radical 3. If we wanted to compare those numbers, we would say, well, -3/2 is less than radical 3. Now we use inequalities to help us order numbers. It says, list the following numbers from least to greatest. So we're actually trying to figure out what number is the smallest, what number is the largest. We talked up top in example 7 about using decimal notation to find the relationship between numbers. So that's how we're going to do this. So -2 is just -2, that's it. So I'm going to rewrite it as a decimal here on the side, -2. -pi, that's -3.142. Radical 2, I need to grab my calculator for that. The square root of 2 is 1.414. 1.414. We have 0, that's easy. And then we have 2.5, which is already a decimal. So now we want to order this from least to greatest. So we want to compare our numbers, and you can compare them one at a time, or you can compare them all together. Well, -2 is greater than -3.14, so we know that that's out for the smallest number. And then that's the only negative number from there on, so we know that -3.14, or -pi, is going to be the smallest. Then the only other negative number is -2, so that's going to be next, followed by the gatekeeper, 0, or the origin. So let's see, that's -2, -pi, and 0. Then we have 1.414 and 2.5. 1.414 is smaller, less than 2.5. So that's going to be our radical 2. And last but not least, 2.5. And now we're going to plot this on a number line. My smallest number is -3, so I want a -3.14. So I want to go down to -4. My largest number is 2.5, so I want to go all the way up to 3. -3, -2, -1, 0, 1. Oops. and 2. It's a big jump. -3, -2, -1, 0, 1, 2, and 3. Again, we go ahead and write it in. -3.14 is a skosh between -3 and -4. It's -pi. -2 is exactly at -2. 0, that one's easy. 0. Radical 2 is 1.414. So that's 1 and a little below the halfway mark. And then last but not least, we have 2.5, which is perfectly in the middle of 2 and 3. So, oh, sorry, let me put that out there one more time. Zoom out a little. So we have our numbers from least to greatest. And we have our number line using all of those values. Now what you could also do is you could have plotted them on the number line first, and then from there say, oh look, that's the farthest to the left, and then so on and so forth, moving up to the right. That works as well. So last but not least, we have our try it problems right there. I'll go ahead and give you a couple of seconds. You can go ahead and pause your video so you can try these problems, and then we'll do it together. Okay, so for our answers, first thing we want to do is we want to find the additive inverse or the opposite of some numbers. And remember, when we're trying to find the opposite, we want to simplify the number that we already have. So when I look at this, I see the double negative, right? The two negatives, the opposite of an opposite, or a negative of a negative. Remember, that always turns out to be a positive. So that value is actually positive 2.7. We're trying to find the additive inverse, or the opposite. The opposite of 2.7 is negative 2.7. Number 2, we have the opposite of -5. So that's like saying negative 5. The opposite of -5 is positive 5. We have our decimal equivalent. Now, a way to use your decimal equivalent if you don't have a calculator, you can do it by hand using long division. So, to remember how in the world to do that, let's zoom in a little here. We're taking 3 and dividing it by 16. So our 3 is on the outside and our 16 is on the inside. And we start by saying, okay, well, can we subtract 3 from this first digit? No, we can't. So then we go on to the first 2 digits put together, the 16. How many times are we able to subtract 3 from 16 evenly? Well, we can subtract it evenly 5 times. 5 times 3 gives us 15, and that's what we're